Hi, welcome to the System Conversation at Cornell University. I'm Oliver Gao, Director of Cornell System Engineering Program. Today, my guest is Professor Darryl Farber, and Darryl is actually an assistant professor with the engineering design in the School of Engineering Design, Technology, and also professional program in the College of Engineering at Penn State University. Welcome back to Cornell, Darryl.
Thank you.
Yeah, so before we start, would you mind, can you talk briefly about yourself, your experience?
Mm-hmm.
Yeah.
Sure. So as you rightly said, I graduated from Cornell.
Mm-hmm.
I graduated with a degree in agriculture and plant sciences. I worked here at Boyce Thompson Institute for a couple of years doing plant molecular biology under Professor Dr. Richard Staples.
Mm-hmm.
Then went to graduate school. I switched to economics and worked on water. Went to Penn State and worked on a project on. It was essentially an engineering economic analysis of water treatment systems for small water systems that were facing Giardia, which is an organism that would cause illness if it was in the water. And that project looked at two different technologies. One was a slow sand filtration. One was a rapid sand filtration. Mm-hmm. There are differences in cost. Slow sand filtration is an older technology that was employed at the turn of the century in large scale in cities like Washington and New York, but also is used in developing nations that for there's low costs. There's low cost to that, but there's high operations. There's a lot of expertise one needs to have to make that system run. And so I looked at the applicability of this older technology for small communities in Pennsylvania. Then I worked for a number of years doing some kinds of economic analysis there, just low-level economic analysis or applied economic analysis. And then I looked at what was then the Science, Technology, and Society program and worked with a number of faculty there, a philosopher, material scientist, and a sociologist that were affiliated with the program. And then there was a challenge for the nuclear industry that I knew nothing about, but I knew enough about economics, and I knew enough about how to think about problems of engineering economy, and I also knew enough about some work in sociology that I could address the problem that they were facing, which was a new technology for spent fuel storage at nuclear facilities. So if you're not familiar with this problem, essentially at the time, the United States doesn't have a long-term nuclear spent fuel nuclear storage facility, where after the fuel is not usable for a reaction in the nuclear reactor, even though it still has plenty of fuel in it, those fuel rods would have been shipped to Yucca Mountain or whatever repository the federal government decides upon. In lieu of that, one strategy was to take the fuel rods and pack them closer together in a spent fuel pool. Well, the challenge of doing that is you don't want to have those rods packing together so that you can have a criticality event where you would have fission events if they were packed close enough. So the question there was looking at alternative materials, essentially a borated steel, a borated ceramic, to try to figure, because boron absorbs neutrons, and the basic question was which should a particular industry, which innovation would be satisfactory for that particular situation. That led to a Ph.D. looking at radioactive waste decommissioning. So I had some now nuclear background, and then I went to look at a problem of nuclear waste decommissioning, literally a back 40 waste site, I was privileged to have an internship at the Nuclear Regulatory Commission for about 6 months. So I lived in Maryland, and worked at the Nuclear Regulatory Commission looking for projects that would make sense for a Ph.D. dissertation. And this one was very good because it had problems of not only it was a fuel fabrication facility outside of Pittsburgh, and there was special nuclear material presumed in these trenches, and the question is how to decommission the site. And there were some choices to be made. They could leave it on site, they could dig it up and leave it on site, and then there was very much a community involvement for different options. So it was a challenge. There was at least 3 entities. There was the challenge was trying to understand what to do, given you had the community, you had the people that lived there, the company that owned the facility, and then the federal government, both the Nuclear Regulatory Commission as well as other aspects of the federal government that were interested in decommissioning what was formerly utilized facilities. That led me to a postdoc at the Kennedy School, where I looked at decommissioning for Maine Yankee. That was a facility that was up in Maine. Went up there, visited that facility, and then after the postdoc, I worked as a project associate visiting lecturer in Singapore at the National University of Singapore in what was then called the Public Policy Program. It was a joint venture with Harvard and the University of Singapore, the National University of Singapore, and that's now the Kuan School. There was an opportunity to return to Penn State in the STS in the Science, Technology, and Society program, and I thought that would be a good idea to do, teaching essentially science, technology, and public policy, and a course on technology assessment and transfer at the time, and then some other courses too. And that's where really I met my good collaborator, Martin Petruka, and we developed some research initiatives on scenario planning and local land use and transportation. And we did a scenario workshop, and that led to some research then down at the Navy Yard in Philadelphia, essentially looking at the interactions between the built environment, the transportation system, and the energy system.
This is very broad spectrum of the experience. That's very impressive. And actually, I think that kind of makes you probably one of the best persons to talk about, you have observed different segments of our society, mm-hmm. right? From agriculture, plant science, energy, nuclear, and of course, social policy, mm-hmm. public policy. So in that sense, what do you view as the key challenges in the areas of your research interest?
The largest challenge is yoking or connecting the insights and knowledge of the people that run large-scale systems with the ability to gain to somehow understand and model those systems so that we can better understand how they may change over time. So as an example, 2017 is fairly different than 1917. But in 1917, we could see the beginnings of of our society today in some forms: electricity, communication technologies, transportation technologies, and over that 100-year period, now significant events occurred during World War II, with regard to operations research, radar, and the atomic weapons that has significantly changed the world. Today, in 2017, we can see the roots, the beginnings of things that will significantly change the world over the next century in 2117. And the question is, how do we really, some of these things are going to offer tremendous benefits to humanity, no question about that, but they also have risks, and the ability to govern the risks that now is not just being generated by labs or by engineers and scientists in the United States. This is worldwide, and our ability to manage our interactions with machines, our ability to understand new life forms and to guard against those, such as disease, emergence of disease, our ability to solve our problems in a peaceful, diplomatic way is our challenges, and we could see that at the local level, we could see that at the regional level, we can see that at the national level, and we see that at the global level. And so that is a large challenge. So how does one really grapple with that? And part of it is identifying what the problems are. Is trying to be able to understand what are symptoms and what may be more generating the problems. And that is both a scientific task in understanding a phenomena, but it's also an interpretive task. So that will raise issues of values and raise issues of culture and the differences of those. I mean, we're not going anywhere. We're all on the same planet here, and our ability to steward the life on the planet is directly related to our well-being, and that seems to be that's a 100-year challenge.
What role do you view systems approach to play in addressing those challenges, and why systems approach?
Well, the systems approach is to do, as you're saying, Oliver, is about at least 50 years old. And one great example of that is a book by Simon Ramo, the aerospace engineer. And in his book, Cure for Chaos, advocates the systems approach to really dealing with complex problems that have multiple dimensions to them. It hasn't worked out all that well, and part of the reason Dr. Ramo understood this also, and this was something that was identified by Dr. Alvin Weinberg, that a systems approach is necessary but not sufficient, and that one needs to really understand the values and how values change, and it's that combination that combination is what we're struggling with right now.
Of course, kind of when we talk about the system approaches, there are different layers and different scales of system approaches, and sometimes it's very easy for people to go at a very big scale, or sometimes at a smaller scale. Right. Maybe I think it will make our conversation a little bit easier by using some of the very nice examples that you have looked at. For example, the Navy Yard project that you worked on in Philadelphia area, and I think you emphasized the approach, the system approach, to look at the interdependencies of a system of systems approach.
Right.
Right. So can you use that example to talk about the systems tools and the system values and system thinking that you applied in that project and the benefit, the advantage of system approach?
Yeah. So the one workshop that we conducted with colleagues at the Technion, Doug Dorey and Yannick Mordecai, was using the object process methodology to identify the connections between, and so although I talked about the larger scale, we really needed to start small because it's just the larger global trends provide the context. And it's this context rationality that one's looking for. And so if one has a sense of the broader context, that informs particular projects to some degree. In this particular case, we were looking at the connection between the transit system and the grid, the PJM grid. And what we did was conceptually modeled the interaction, particularly with regard to energy storage. And that was a workshop, as an example, that was a workshop where we had participants from SEPTA, which is the Southeastern Pennsylvania Transportation Authority, and and PJM, and the sitting at a table, and what we did was try to bring out their tacit knowledge, their understanding of how the systems were connected. And then we would take that knowledge and transpose it onto a model-based systems engineering. So this idea of knowledge transfer and a knowledge management problem in this small aspect is what we were driving at. The value of it was the participants themselves engaged in conversations about strategy that they would not have otherwise had. So our role as academics, we played a catalytic role in having that kind of conversation and process for thinking through strategies and decision making, and that the outcome itself was a byproduct, but the main value is that the practitioners who would not normally talk to each other talked to each other. They found out things about their systems that in relationship to the others were things that they knew but were enriched by that conversation, and that was a value. And what it also pointed out was the tremendous difficulty in establishing a language for communication. And in this small example, it really was something that was evident, that using the object process, using the systems methodology, that provided a tool for bringing the language, trying to make the languages commensurate. It was like a translation tool, but it's difficult. That is an extraordinarily difficult problem, and it also hints at the problem of how advanced natural language computational tools could possibly be used to extract meaning from text, dialogue, and that's in the future. But it's there because right now it's a process that to do that at large scale it's just not feasible. It's not a feasible process right now. So you have to have very constrained, particular circumstances that you're looking at that could get to do that.
So you and me, we both work in this very important area, infrastructure systems.
Right.
So our society is essentially supply and demand.
Yeah.
While in the its infrastructure is really the critical linkage that bring the different supplies to meet all these various demand.
Right.
Right. So in this aspect, you have been looking at this interdependency. For example, between the built environment,
right,
the energy system, the transportation systems, of course, our daily life.
Right.
Right. I think somewhere I was reading your work, and I think you mentioned some emerging themes related to our critical interdependent infrastructure.
Right.
I think you are talking about the vulnerability of our aging infrastructure.
Yes.
And I think you talk about integration of technology
right.
in the existing infrastructure.
Right.
With all this kind of technology and community co-evolution.
Right.
So the lifestyle
right.
and the value system
right.
Will change.
Yes.
Of course, in the end, when we think about infrastructure, investment infrastructure is not about you go out as a household, you buy a car.
Right.
Right. It's
yes.
really right. It's you. The government
yes.
goes out and procure something through very complicated procedures that will last
right.
For decades. So I think your own words is kind of the fourth theme is about financial innovation.
Yes.
I think those are very good summaries of these key emergent themes. Can you talk more about those themes related to our infrastructure systems?
Sure. Well, just as a broader context, think that there's a meme, or there's a lot of work now on smart or intelligent cities, and because of the growth in populations there, on the one hand, and then on the other hand, that the American Civil Engineering Society, AACE, yes, and gives the U.S. infrastructure a grade of D+ in the latest report card of 2017. And in that report card, it states the needs are something on the order of $4 trillion. They have in the report card the funding request of $2 billion, which leaves about a $2 trillion shortfall of funding. And the current administration is looking at $1 trillion of infrastructure investment, and the financial model is not clear what that will be. So just by the numbers, we have the vision on the one hand of a smart, connected city, and then we have the reality of D+ infrastructure. And if you look at the numbers with regard to the civil engineering numbers, they're a couple $1 trillion off. There's a couple $1 trillion in deficit. So what we've done over the last number of decades is we've disinvested in our infrastructure, and it's going to take decades to reinvest in our infrastructure as a common resource. That provides the broad context for this. And in that context we would like to have infrastructure that is, I'm going to use, robust and resilient, and there are different communities will use those terms differently. One would like to have infrastructure that is environmentally responsive infrastructure. Sometimes it's termed sustainability, sometimes it's termed regenerative infrastructure. We want infrastructure that's secure. We want to live in a society with infrastructure that is consistent with our values of the society as a democracy, and that there's new technologies, and we see them being integrated into our infrastructure in ways that as sensors, that the people that invented that infrastructure would not have thought of those uses. So the uses itself are emergent. That provides a lot of possibilities for how the future would unfold. And one needs to be able to, as a society and as decision makers, to really think through a number of possibilities, not infinite number of possibilities. It's just too much for to be able to effectively decide upon and then also implement. Implementation is a critical aspect. So it's not just simply coming up with the strategy, it's also being able to implement and operationalize the strategy. And those things, so there's a role for theory, but there's also a tremendous role for practice, and they have to inform each other. One or the other is not sufficient. They really need to inform each other. And this is the role academics can play, because we maybe have it. We have the ability. Well, we have the opportunity to think through in a longer term perspective than the system practitioners who, and they keep the trains running on time, they keep the lights on, and the buildings warm in winter and cool in the summer, and they make that happen. So there's a role for both.
I saw that you are now heading these programs, the engineering systems and policy program at Penn State.
Yeah.
So that's apparently a very good reflection of your view of, for example, engineering education, right? So I also noticed you had a publication, probably I think maybe 10 years ago, that was Systems and Scenarios for a Philosophy of Engineering.
Right.
And these are really hitting all the key emerging complexity that future engineers need to face and need to solve, and even need to play a leadership role in dealing with these issues. So, can you talk more about your engineering system management and policy program, and also your I think kind of your perspective of how engineering, social science, human factors, how they interact, and how these together, by integrating these things together, that will benefit the education of our future engineers, especially here at Cornell. We have this system engineering program, and that's why I was so excited about reading these things, because you can see that our values and our views overlap so nicely. So what should we equip our future engineers or system engineers with?
The paper that you mentioned, I was privileged to work with two visionary engineers as co-authors, Dr. Martin Petruka and Dr. Akhilesh Latakia. And really through discussions with them, we were able to think through that paper. And with the Engineering Systems and Policy program, we've thought about that for a number of years. It's still a program that is in progress, in genesis, and we thought about what the elements would be of that program, and I came up with a list of 7. Well, I think we came up with a list of 7 names. I sent it around to a few of our advisory committees. So we established an academic advisory committee, an industry advisory committee, a council, advisory council, sent them the names. Then Penn State has a honors college, a Schreier Honor College, and there were a number of students there who have gone on to similar programs at other universities, MIT, Carnegie Mellon, and Berkeley, and I had sent them, they had graduated, and I had sent them the list of 7 of the possible names for the program that we thought up, and they came back with the 8th, which was Engineering Systems and Policy. So it's a wonderful title, and it was nice because the students who came up with the name, and they were the ones that in a way that it really reflected both the engineering element and the policy element in a combination that in our 7 we had not thought of. So that was a little bit of the history of that. There's elements of that, of the proposed elements of the program are there's you can think of it as an embedded set. So the large part is this global trends as an example, and working global trends has been done, and particularly scenario work, scenario planning, which has been done at Shell and at RAND, the RAND Corporation. In fact, it began with Project RAND and Herman Kahn on scenarios, and that Shell picked it up to think through their planning for energy, their planning purposes for energy futures in the mid 1960s, and they were looking at some forward-looking studies. But they recognized that the managing directors recognized that the world was they needed to think about this beyond simply production planning and beyond simply financing, that they really had to think about a changing world that would be discontinuous in some elements. And this is the approach is to look for things that are continuous and things that may be trend breaks or game changers, as it's termed in one of the strategic reports called Global Trends 2030 Alternative Worlds. Essentially the architecture, it's a transdisciplinary architecture that we've created, where the large part is the global trends. Embedded in that is policy aspects, global policies, as much as there are things as global policies. An example would be the nuclear non-proliferation regime. The complexity, so there's the policy aspects or the regime aspects. There is a methods aspect, both quantitative and qualitative methods, narrative methods. And then there is a complex systems aspect to this. And that's something where complex systems theory, you can trace that back. It's got a number of roots. Cybernetics in the 1940s is one. Herbert Simon's work on the sciences of the artificial is another in the mid-1960s. And now it's the Santa Fe Institute and their complexity sciences. As an example, there's also a New England group that works on complexity sciences and systems. The difficulty is that, as you mentioned, that systems engineers have been, and science in the 20th century has been amazingly successful. And that's been the product, to a large extent, of the strategy of reductionism. And this is something that was raised by P.W. Anderson in his paper, More is Different. And it's also raised in a book by Robert Laughlin about, he has a nice way of describing it, the age of emergence, and this is in the papers, the age of emergence and the age of reductionism. And the idea of emergence Nancy Levinson of MIT describes it well, is that the shape of an apple, you can't find the shape of the apple in the particular cells of the apple. Now, of course, it is in the cells in the sense of the genome, but how the genome gives rise to the phenotype, that is not necessarily clear, and it's one of the NSF's grand big idea challenges. So similarly, it's this idea of going from, in this particular case, the information, the coding, to the information to its I'm going to say instantiation in the world. I'm not sure that's quite the right way to phrase it, but you get the idea.
Yeah, I got the idea.
Yeah.
I kind of it's influencing information from genome to phenome.
Mm-hmm.
Of course, now scientists are talking about the exposome, right? So kind of how, from a health point of view, right? Of course, genetics affect a lot
Right.
of human health, but when it comes to phenome, and then we are exposed to the built environment, there is exposome. So
Right.
all these things together, that could be very interesting. And also, you mentioned the work at Santa Fe Institute,
Mm-hmm.
and also at the not North England,
The New England.
the New England
Yes.
System Research Institute. Actually, we had both David and also Brian talked in this seminar
Wow.
series. So some time
Yeah.
ago. And I think we're towards end, we're running out of time. However, I do notice that in the material I was reading, you had Norman Augustine
Yes.
as the speaker,
Yes.
in your program.
Right.
So again, he also talked in this seminar series.
Oh.
I guess probably 4 years ago.
Oh, great.
And
Yeah.
I invited him here after actually one of the CISA meeting where he talked about the system challenge.
Right.
Yeah, that CISA meeting was at I think it was at MIT.
Mhm.
So, but I think anyway, I think in one of the material you quoted what he said.
Mm-hmm.
And engineering teaches us what we can do.
Right.
The arts and the humanities teach us what we should do.
Yes.
So I think that is really kind of your, the conversation with you today. I think that is a very good reflection of when we look at social technical systems.
Mhm.
We should not just look at the engineering part, the technical part, and actually the social part, the human part. Could be even more, actually much more important. So thank you, Darryl. That was great to talk to you.
Mm-hmm. I think we covered a good amount, Oliver. Thank you very much.